Electronics in cars, a lot of cars, metal cars, use the chassis as a return, okay, but it's there. You have to know it's there, and if you have high frequency stuff, high frequency fields, and the wire that's feeding it from one side is not against the metal of the car, then you have a big gap between your outgoing wire and your return flow. If there's a big gap, you get you create a magnetic field. Or you create electric fields. If you put them together better, I'll show you that. So this is a two-wire interconnection, very simple. The source has a load, and the current that flows we call the difference remote current. This is the intended current, the current that was designed, probably measured. Somebody will check it, so we never have anything to do with it by EMC. No problem, difference remote. But if you have extra connection, in this case a ground connection from the source and load, but the ground could also be a second cable going the same way as the other one, then it's possible that some of the return current decides to go down to ground. Why? Depends on the geometry. And because geometry is a big issue in EMC and interconnections, I sometimes tend to say that EMC is something mechanical. Mechanical engineering. Geometry of the interconnection is very important. Okay, this common mode current is usually small. There's the amperes going up there, and here's a few milliamperes, microamperes here, going to the ground or another cable. But if the current goes here, due to this Kirchhoff law, that means that the differential mode set is not identical. The current going out is a little higher than the current going back because some of it goes another way. So if you measure around the cable with the current clamped like that, you can measure the same common mode current on the cable, and that's why you can make the picture like this. And so you see common mode current also flows in loops. It's a current, it doesn't know it's common or differential, so it flows in loops. All current do that. Okay. That's a definition. Somebody else could make them. That means it could be a neighbor generating the common mode current, and you would have the current. And then you would probably have an immunity problem if there's any interference. And then 98% of the EMI problems is common mode, maybe even 99. So if there's a problem, EMI, start with the common mode, differential mode comes later. Okay, now interference. Circuit 1, cable 1, circuit 2, cable 2, and somehow the circuit, what circuit 1 produces, gets into circuit 2. That can be done in different ways. It could be that there's a connection to ground or so, and that some of the current really flows on the cable, on the grounding cable, to the other circuit, and then flows through the other circuit and creates some voltages there. It's also possible that you generate fields, electric fields, magnetic fields, which then go through the air from one loop to the other. You see the circuit has a current loop, two current loops, and they communicate through these fields. They're not supposed to, but they will. Okay, that brings us to the second law, Kirchhoff law, which is the voltage law. The voltage law says, okay, I have a circuit here, a loop with that much elements in it. The sum of voltages should be 0. That's what this law says. But there we can put a question mark, because that's not quite true. This is only true if all the fields are inside the components, which is some assumption in network theory. Okay, we can do this. If all the fields are concentrated in the elements and the wires are ideal, then yes, then we can say it's 0. But in practice, if you have a loop and you create a field in it, or you change the field in it, an external field, it will create a voltage. And that's Faraday's law. Faraday's law says, okay, the voltage you will see in this loop, so the sum of voltages is not 0, but equal to this voltage. The change of the field, flux change, divided by the time it takes to change it. And the bottom part is very important, transition time, because in the past, very slow logic, slow, low frequencies, the transition time is long. So you get a big number in the denominator here, so this voltage is low. Let's say in an old printed circuit board with TTL logic, you had maybe 3 millivolts of noise, being the flux change divided by the transition time. And now everything is 1,000 times more faster. Instead of microseconds, you have now nanoseconds. So this is 1,000 times smaller, so the voltage becomes 1,000 times bigger. If you had 3 millivolts in the past, you take the same printed circuit board with a new device, and instead you have 3 volts, and then probably won't work. So that can happen. It has happened in the past that new circuits became available with the same number, you put them in, and now suddenly it doesn't work anymore. Well, that's this. There's a minus sign come to this. Okay, self-induction. We have we need a loop, a wire loop. This is the wire loop. I'll show you the scope pictures. Okay. This is my square wave. Okay. Not yet working because I had a power supply which is now this. No work. Yeah. Way too fast for this system. So then the green one is 1 inch of the wire. Okay. Okay, what do we have? I have a generator here, oscilloscope. The cable from the generator goes through this long red wire. Goes through the wire and then to another cable to the second channel. So the top channel is this side, the bottom channel is this side. And, well, you see the difference. It's not the same. It's funny. Make it bigger, it gets worse, make it smaller, it gets better. I'll expand it a little bit. Let's a little bit faster. Then you look at one of these transitions. Okay, this is one transition going up, and then further down there's one going down the same. Okay, this is my my wire loop. See, if I make it nice and big, it's a big spike, and a compatible thing on the bottom. The way to make it small, become faster and small. Now what happens here? Okay, this square wave is in this case 3 volt peak square wave. Put it on a wire. In the generator there's a 50 ohm resistor, and on the load on my scope is also 50 ohm resistor. So there's some current flowing here. In a stable situation, say here or here, there we have halfway the voltage. So 1.5 volt from the 3 volts that's initially. Well, as soon as the 3 volt gets here, it sees my wire. It's a big loop, and to get any current in here, I need a field. Current and field is identical. Look at Maxwell equations. No field, no current. No current, no field. So current can only flow as soon as there's enough field around it to make it flow in the wire. So the current has to be built up. It takes time. It takes time to fill this loop with field. And that's the time it takes. So initially you get 3 volts. And then it goes down in an exponential curve to the steady state value, 1.5 volts. So initially it's 3 volts. Well, my scope is not fast enough to really see the 3 volts, but you can see at least the difference. It's trying to get the 3 volts and then going down. And here, initially there's no current. So 0 voltage. And then it takes some time to get the curve to go.